Hello everyone. In the previous lecture we started our discussion of polymer dynamics, and we specifically focused on dynamics of polymer chains which are unentangled. We looked at two different models, one which was applicable for unentangled polymer melts, and that was the Rouse model, and the other one which better described the behavior of polymer chain dynamics in dilute solutions, and that is the Zim model. In today's lecture, what we will do is focus on the dynamics of entangled polymers. So, entangled polymeric chains are basically much longer in nature. So, if the polymer chains are long, then typically they will tend to entangle with each other, and the dynamics of such entangled polymer chains is quite different from that of unentangled polymer chains. In today's lecture, we will primarily focus on dynamics of entangled polymer chains in melt like state. So, we will introduce the concept of entanglements in melts. We will specifically focus on a concept which was proposed by Sir Sam Edwards, and that is the tube concept, and we will discuss how the system of entangled polymer chains can be described using this tube concept, and we will also talk about the related parameters. And thereafter we will see how this tube concept can be used or was used by Dijon to propose a model for the dynamics of entangled polymer chains, and this model is referred to as reptation. So, we will focus on reptation thereafter. If we talk about entanglements, so entanglements can be thought of as what is called topological restrictions that the presence of other chains imposes on a given chain, because the chains cannot cross each other. So, since the chains are formed by covalent linkage of monomeric units, if two chains get, let us say, entangled in a way, then they cannot cross each other, and that restriction or constraint imposed by the presence of surrounding chains on a given chain, that can be thought of as representing entanglements. These entanglements, as we discussed, are topological constraints. It probably is much easier to visualize this using some simple cartoons. So, we can think of consider the two chains that are shown here, one in red and the other in black, and if we consider the motion of the black chain here, and let us say if the black chain is moving to the right, then a point will come when this portion of this black chain will be restricted from motion because of this portion of the red chain. Since the black chain cannot cross the red chain, that constraint will be imposed on the motion of this black chain by the presence of this red chain. So, this is a very simple kind of pictorial representation of what an entanglement effect might be, and here we have just two chains. Now, imagine if the case is more complex, where we have the presence of large number of chains and all of them entangled with each other, which might be the case for melt of long linear polymer chains. So, if we have such a complex case where there are multiple entanglements present, then what one can do is again in a simplified manner represent the presence of entanglements as constraints imposed by the surrounding chains on a given chain. If we again consider let us say a chain that is highlighted in this diagram, and if we consider all the dots that are around this chain to represent the constraints that are imposed by the surrounding chains on its motion. Okay. So, if that is the case, then what we can say is that this polymer chain is not free to move about or diffuse in any which way that it likes. Its motion is constrained by the presence of all these dots, which represent the effect of the chains surrounding this highlighted polymer chain. So, all these constraints restrict the motion of the diffusion of this polymer chain, and due to this restriction, this polymer chain that we have, that can only move in a way which avoids all these obstacles that are present, and one way to accomplish that could be that if we consider this as the tail end of our polymer chain, then the motion might be thought of as starting where the tail retracts in a way. So, this part of the tail retracts in a way so that some kind of loop or kink is formed, still respecting the constraints imposed by the surrounding chains, and this kink or loop is then moved, or this kink moves along the contour of the entire given chain all the way towards the head of the chain, which may be here, and while moving it's respecting all the constraints that are imposed by the surrounding chains. So, this is a very simplistic picture, because as the any motion that takes place within the given polymer chain, the surrounding chains will also be moving during that time. So, the nature of the constraint imposed itself might be a bit dynamic, but for simplicity we assume that we have these fixed obstacles and polymer chain motion takes place through, let us say, a kink or a loop developing at one end and then getting transported along the contour to the other end. Then after some time the chain conformation might look something like this, where part of the tail has retracted up to this point and the head has extended here. As we discussed, the polymer chains in an entangled polymer mass, the polymer chains are constrained by the presence of surrounding chains, and the effects of entanglement are especially important for long polymer chains. So, if the polymer chains are short, the entanglement effects either will be not present or will be small. So, if on the other hand the polymer chains are quite long, then a single chain might be entangled at many different places, and the effect of entanglement on the dynamics of polymer chain will be highly pronounced, as we will see. Next, what we will do is try to discuss a concept which is called the Edwards tube model, or the Edwards tube concept, which simplifies the description of motion of a polymer chain in the presence of all these surrounding constraints. The concept of entanglement was treated by proposing the tube concept by Sir Sam Edwards in the 1960s, and in this model the key points of this model are that we have a given chain and it is surrounded by a bunch of other chains, so that the motion of the given chain is restricted and the path that it can take is also restricted by the presence of the other obstacles around it. The presence of the surrounding chains is modeled as a constraint on our given chain. Okay. All the, let us say, monomeric units in a given chain, they are acted upon by some kind of constraining mathematical potential which represents the constraints imposed by the surrounding chains. If we consider, since these are mathematical functions and initially a quadratic kind of constraining potential was considered, if we consider the regions in which this constraining potential has potentials on each of the monomers exhibits minima, then that path is what is defined as the primitive path. If the minima of the constraining potentials they lie along what is called a primitive path. So, this primitive path is the region of space which corresponds to the minima of this constraining potentials representing the surrounding constraints. And due to the presence of surrounding constraints, what is assumed is that the polymer chain itself is constrained in a tube like region. Okay. And this primitive path kind of represents the center of this tube like region, and the polymer chain itself is bounded by this tube like region defined by the presence of the surrounding chains around this given polymer chain. So, again if we go back to the cartoon that we had drawn earlier for representing entanglements and constraints, and if we consider our highlighted polymer chain here, then we can think at this particular instant when this snapshot is considered, we can consider the polymer chain to be confined to some kind of a tube like region that is defined by the presence of other constraints all around this polymer chain. So, roughly if we consider this kind of a tube, what we can say is that the motion of our polymer chain is constrained to happen in a some kind of a tube like region, as I am roughly drawing here. And so, this is one end of the tube, this is the other end. And what this Edwards tube concept states is that the given polymer chain is confined to a kind of a tube like region, and the central a path denoting the center of this tube like region will correspond to the primitive path where the constraining potential will have their minima. It should not be it is not the case that the length of the tube like region corresponds to the contour length of our polymer chain. So, within, if we consider, let us say, small section of this tube like region here. So, let us say if we consider this section here, small portion of the tube like region. So, the polymer chain in here itself can adopt different conformations. Okay. So, the primitive path might be somewhere along the center. The polymer chain itself can have different conformations inside. The contour length of the polymer chain usually will be much larger than the length of the tube that we have, confining tube that we have. So, that is the Edwards tube concept, and in this model that was proposed by Edwards, the monomers on the given polymer chain, they are constrained to stay close to the primitive path that defines the center of the tube, but they are not completely bound to the center. So, they can of course fluctuate around this central primitive path due to the thermal effects. So, thermal fluctuations are allowed, although monomers the potential tries to constrain them along the primitive path or close to primitive path, but since they will be thermally fluctuating, so they will adopt conformations that will be centered around the primitive path, but will not necessarily coincide with the primitive path. If we consider the tube, the confining tube, then what we can say is that we can quantify its width of the tube by a quantity known as a tube diameter, and typically represented by A. What this tube model proposes is that along the tube, if the chain motion is happening along the tube, then it is not restricted at all, because along the tube entanglement effects are not there. The tube is defined by the surrounding constraints. So, within the tube the chain is free to move. However, perpendicular to the primitive path, which marks kind of the center of the tube. So, the motion perpendicular to this primitive path, that is constrained, and monomers motion perpendicular to the primitive path is constrained to happen on an average up to a size characterized by this tube diameter A. So, the monomer displacement that is perpendicular to this primitive path, that is constrained to an average distance, say it can happen by distance more than A, but on an average that displacement will be. Next, if we consider this tube diameter that we have. So, since tube diameter is a quantity which characterizes the entanglement effects, what one can say is that the number of monomers that are present in a given entanglement strand, that will also be equal to the number of monomers that will be present in a polymer strand of length equal to the tube diameter. So, in other words, the tube diameter, the size A, corresponds to the or is of the same order of the as the length of an entanglement strand of the polymer. So, when we say an entanglement strand of the polymer, it is an average measure of the size of the portion of the polymer chain between two entanglement points. Okay. So, polymer chain given for long polymer chain in general will be entangled at different many different points along its backbone, let us say. So, on an average, the length of the polymer portion of the polymer chain between two entanglement points, that is the size of the entanglement strand, and the entanglement strand itself is the portion of the chain between any two entanglement points. So, what we are saying is that the tube diameter size, this A, is of the same order as the size of an entanglement strand of the polymer chain. So, that again itself suggests that number of monomers, or the let's say number of Kuhn monomers that is present in a given entanglement strand, that will be equal to the number of Kuhn monomers that will be present in a polymer chain having or portion of the polymer chain having length A. So, if we make that observation, then from there we can another observation is that since we are talking about the melt state. So, in the melt state we have already discussed previously that the polymer chain assumes ideal chain dimensions, because the excluded volume effects are effectively screened in the dense melt state. So, the chain dimensions correspond to the ideal dimensions. The relation, the fact that any polymer strand of size A, which is a tube diameter, will contain any number of Kuhn monomers, and the fact that the ideal chain dimensions will be adopted by the polymer, these two can be combined to relate the quantity A with the quantity Ne, and that we can do simply by writing this expression: A will be of the order of B times Ne to the power half. So, this comes directly from what we have studied earlier about statistics of or the size of ideal polymer chains. So, we studied that if we have any ideal polymer chain, that can be represented as an equivalent freely jointed chain, and there the mean square end to end distance, that can be represented as NB square, where N is the number of Kuhn monomers in our polymer chain and B is the Kuhn length. What this suggests is that the root mean square end to end distance, which will be the characteristic size of the polymer, that will be square root of N times B. So, that is exactly what we have written here. This Ne to the power half is square root of Ne, and Ne is the number of Kuhn monomers present within our entanglement strand, and we say that the entanglement strand has an average length which corresponds to the tube diameter A. So, so this same relation has been reformulated for the case of our entanglement strand and tube diameter. So, we see that this tube diameter A is of the order of B, which is the Kuhn length times square root of the number of Kuhn monomers present in a given entanglement strand. So, again it should be emphasized that Ne is the number of monomers or monomeric units present, Kuhn monomer units present in an entanglement strand and not on the full polymer chain. A given polymer chain will be composed of many entanglement strands, and Ne, this number corresponds to just a Kuhn monomer's single entanglement strand. So, now that we have this expression, we can think of our confining tube. So, the tube that is confining our polymer chain, we can think of it as being composed of N over any different sections. So, the tube confines the entire polymer, so it corresponds to a total let us say N number of monomeric units. So, this N corresponds to the number of monomers present in the entire polymer chain. Ne is the number of monomers in a given entanglement strand, and since the size of an entanglement strand is of the order of the tube diameter, we can say that each of these sections has a size A and each contains any monomers. So, if we consider our confining tube, of course it might have a much different shape than this, but just as an example, we can consider the entire confining tube as being composed of different sections. If each of these sections has a length A, which is equivalent to the tube diameter itself, then we will have N over Ne such sections. The reason for that is since this length is A, this will have approximately Ne number of Kuhn monomer units in here, and since the total chain contains N Kuhn monomers, the number of such sections will be given by N over Ne, and each section contains any monomers. What we can say is that the entire polymer chain, its dimension can be represented using our equivalent freely jointed chain consisting of N Kuhn monomers and having Kuhn length B, or equivalently we can also write its dimension to correspond to the fact that it consists of n over any different entanglement strands, and each entanglement strand has a length a. We can also think of our entire polymer chain as being a random walk or a freely jointed chain consisting of segments having length a and a total of n over any such entanglement strands present along the polymer chain. If you use both these cases or considerations, then the polymer chain dimension, let us say r, that can be represented in two different ways, either by this or by this. So, the second one is just a representation where we are considering the polymer to be an equivalent freely jointed chain having a cone length b and number of cone monomers n. In the first case, here we are considering the polymer to be again a kind of freely jointed chain or a random walk where the size of a given segment corresponds to that of an entanglement strand A, and we have the total of n over any such entanglement strands, and all these entanglement strands together constitute a kind of random walk which leads to our entire polymer chain. So, since both these are equivalent, we can say that the polymer chain dimension can be represented by either of these relations, and what we can infer from these two is that this ratio n over any will be of the order of b square over a square times n, and that can be done simply by rearranging the terms here and squaring this n over any to the power half. That is what we obtain for the chain dimension. We can represent it in two different ways by considering a chain to be a random walk either of the cone monomers or of the entangled strands themselves. Now, average contour length of the primitive path. So, we have a primitive path defined. So, the contour length of this primitive path that we can represent simply as a times n over any. So, we have considered our tube to be divided into n over any different sections, and each section has a length a. So, the total contour length of the primitive path will be simply the product, which is a times n over any. Now, this n over any that we have here, that we already see is of the order of this ratio. So, if we substitute that, then we get this term. So, we are substituting n over any by b square over a square times n. So, we get this term, and then finally from here we can simplify to this term, because we already know that a, which is the tube diameter and which is also the length scale of an entanglement strand or dimension of an entanglement strand, that is just b times n e to the power square root n e to the power half. So, that gives us the dimensions of the primitive path, and we already have the polymer chain dimensions here. Next, let us consider another concept that is important here, and that is referred to as the rubbery plateau region. Okay. So, if for long linear polymer chains where the number of cone monomers n is much larger than the number of cone monomers present in a given entanglement strand. So, if the entanglement effects are strong, what is observed is that if the stress relaxation modulus is obtained as a function of time or as a function of frequency equivalently, then what is seen is that there is a wide region or wide range of time scales or frequency scale over which this stress relaxation modulus actually shows an almost nearly constant value. So, this region where the stress relaxation modulus is nearly constant is called the rubbery plateau region. Value of the modulus in this rubbery plateau region is referred to as the plateau modulus. This plateau modulus can be represented, we will not go into the details of this, but it can be represented to be of the order of this ratio, where rho is the density of the polymer melt, R of course is the gas constant, T is the absolute temperature, Me is the molar mass of an entanglement strand. So, it is called the entanglement molar mass, Me is called entanglement molar mass, and it can be represented as Ne times m naught, where m naught is the molar mass of a cone monomer. So, a single entanglement strand has any number of cone monomers and n a subscript e number of cone monomers, and each cone monomer has a molar mass m naught. So, entanglement molar mass will be simply the product of these two. So, now if we consider the plateau modulus as defined previously and the entanglement molar mass, this entanglement molar mass, the expression we can simplify further. So, here what we have done is in the cone monomer molar mass, that we have represented as a product of these three terms. So, here V naught is the volume of a given cone monomer, rho is the overall density of our polymer melt, and n is the Avogadro number that has to be present, because we are talking about a molar mass, that is the mass of 1 mole of cone monomers. So, this V naught is the volume of a single cone monomer and rho is the density. So, this product will give the rho times V naught will give the mass of a single cone monomer, and if we want the mass of 1 mole of cone monomer, we need to multiply by the Avogadro number. So, if we substitute this expression for Me, which is Ne times V naught times rho times n Avogadro, if we substitute this here, then the expression for the plateau modulus can be simplified, and we have this where the rho will cancel, and this R divided by the Avogadro number, that is simply the Boltzmann constant. So, if we make these simplifications, we get this expression for our plateau modulus, and which can again be further simplified, because this Ne is this ratio A square by B square. So, the way we had defined let us say A as being B times square root of Ne previously. So, this A was defined to be of the order of B times square root of Ne. Then from here, if we square root of Ne is A by B, and then taking square on both sides, Ne will just be A square by B square. That is what we have substituted here, and here in this last step we have just multiplied and divided by B to get these two. So, this term is just B cube by the volume of a cone monomer, and B cube is the cube of the length of the cone monomer, and this second term is just KBT divided by A square B. So, the plateau modulus in a simplified form can be written as is shown here. Next, one last concept or parameter related to the entanglement is what is called the number of chains within a given confinement volume. Since our tube diameter, which is the confining tube, the tube diameter is represented by A. So, the confining volume we represent by cube of this. So, the confinement volume will be A cube, and we are trying to find out the number of polymer chains present within this confinement volume, and that number is represented as PE. So, it is the number of polymer chains in the given confinement volume. So, the volume that we are looking at is A cube, and the volume of a single entanglement strand, that is Ne times V naught. So, V naught is the volume of a cone monomer, Ne is the number of cone monomers in an entanglement strand. So, this product, this will give us the volume of occupied by a given entanglement strand. So, this ratio gives us this quantity P that quantifies a number of entanglement strands present within a given confined volume A cube. Now, again previously we have just discussed that A is given by this B square root of Ne. So, if we substitute that, then instead of A cube we will get B cube Ne to the power 3 by 2, and since we have an Ne in the denominator here, that will cancel and we get B cube over V naught Ne to the power half. So, that is the expression for P that we get. So, finally, what we need to understand here is that the plateau modulus G is something that is experimentally measurable, and if we have the value of plateau modulus, then other parameters related to entanglement such as Me, the entanglement molar mass, Ne, which is the number of cone monomers in a given entanglement strand, and P, which is the number of, let us say, entanglement strands present in a given confined volume A cube, these can be obtained directly, because the G, which is the plateau modulus, can be measured, and once G is measured, Me we can obtain from this expression, and once Me is known, then Ne we can obtain from this expression or this expression, either one. This will give us Ne, and once Ne is also known, then from these expressions we can get Pe. So, all of them can be obtained. And if such calculation measurements of Plateau modulus and from their calculation of Pe is done for different linear flexible polymers in melt state, then what is found is Pe is found for most cases to be close to 20. So, Pe is found to be close to 20 for flexible polymers. So, this condition Pe being close to 20, that defines what is called the overlap criterion for entanglement in polymer chains. So, now that we have discussed the tube concept and the associated entanglement parameters, let us now move on and see how the dynamics of polymer chains within the confining tube like region can be studied. Polymer chain motion in a melt, that is a many body problem at the first glance. The reason for this is a given polymer chain, if it is moving, its motion depends on the presence and the corresponding motion of many other polymer chains surrounding it. And since we have it is a dense system and the polymer chains are long, if we try to study the dynamics directly as a many body problem, it will be a very complex problem to study, and it might not actually be amenable to solution as well. One elegant approach that was proposed to study the polymer dynamics of polymer chains, entangled polymer chains, was that by P.G. Dijen, and this approach makes use of the Edwards tube concept that we have already discussed. And here the main point is that for any given polymer chains, the chains around it again impose constraints, and the constraints are imposed such that the motion of the given polymer chain is restricted to in a confining tube, and as the chain moves, of course the confining tube also moves along with the chain. Dijen, who actually won a Nobel Prize for his contribution to important contributions to polymer physics, he used the Edwards tube concept to simplify this many body problem, and proposed that the chain motion can be considered to be restricted to the tube like region. Any model of entangled polymer dynamics which uses this tube concept comes under the category of tube model. So, the model proposed by Dijen initially is one of the simplest tube models, and it is called the REPTATION model, and it is a simple tube model proposed by Dijen. And here what is assumed is that if you have a long linear polymer chains present in a melt state and highly entangled, then their motion takes place in a manner that can be thought of as analogous to the motion of a snake that is just slithering around various obstacles. So, if we consider, let us say, a large number of snakes in a given pit. So, the way the snakes, so of course, if a lot of snakes are present in a small volume, one can think of as the snakes as being kind of entangled with each other. So, the motion of the snake will be a slithering kind of motion where it traverses, making sure that the obstacles present by the other snakes are avoided. So, it takes the slithering kind of motion, and that motion is what inspired this term reptation. The origin of this term reptation is reptile. So, it is a reptilian slithering kind of motion, that is what one can visualize as this reptation model to be like. Now, getting to the mathematical aspects, the motion of polymer chain within this tube. So, if we are considering the confining tube as proposed by Edwards, and if we are considering the motion of polymer chain within this tube, so within this tube the motion is actually not constrained. The constraints are such that they restrict they are kind of restricting the motion to within this tube, but the motion within this tube is actually unconstrained. So, the curvilinear kind of motion within this tube can be characterized by a curvilinear diffusion coefficient dc. dc can be found out easily because within the tube the motion is unconstrained, the entanglement effects are not there. So, one can describe the motion simply as a kind of a Rouse motion of the polymer chain, if we are looking only at the motion along the tube. So, for Rouse motion we already discussed in the previous lecture that the diffusion coefficient simply is given by kBT over n times zeta, where n is again the number of Kuhn monomers present and zeta is the friction coefficient corresponding to each monomeric unit. So, we within the or along the tube, the chain motion is actually not affected by entanglements, and we can say that the Rouse diffusion kind of model describes this motion, and the diffusion coefficient we can obtain from that model. Next, if we consider the time scale. So, in reptation model, the reptation time is defined as the time required for a given polymer chain to come completely out of its original tube. So, at any instant, if a polymer chain is present inside a certain confining tube, and if we consider now this tube to be fixed and the polymer chain slowly diffusing out of it. So, the time required for the entire polymer chain to diffuse out of the original tube that it was present inside, that corresponds to the reptation time. And of course, as the polymer chain moves out, it will create its own new confining tube around it because of the presence of the obstacles presented by the other chains. But the overall time it takes for a given polymer chain to come out of its original tube, that corresponds to the reptation time, and that we can order of this reptation time can be obtained simply as the ratio of the square of the primitive path length. So, the primitive path length corresponds to the, let us say, contour length of our tube, and so ratio of the square of the primitive path length and the curvilinear diffusion coefficient, which corresponds to the diffusion coefficient of the polymer chain within the tube. So, the square of the length scale traversed by the polymer chain divided by the corresponding diffusion coefficient for that motion. So, if we again simplify this, if initially in this lecture we had discussed that the primitive path length, which will just be A times n over Ne, that can be written in this format, and dc of course we have already written like this. So, if we substitute them and take the ratio, we get this expression for the reptation time, and again we can just multiply and divide by Ne square. So, we get this expression where we have this kind of a cube dependence of this reptation time on the number of Kuhn monomers present in our polymer chain. So, now if we again this is the same expression rewritten here, the reptation time expression that we just discussed. What one can see from this expression is that and this is as predicted by the reptation model of Dijon, what we see is that reptation time actually scales as cube of the molar mass of the polymer chain. And the reason for this is that the number of Kuhn monomers present in a polymer chain, that will be directly proportional to the molar mass of the polymer chain. So, since the reptation time scales as cube of the number of Kuhn monomers in the polymer chain, it will also scale as cube of the molar mass of the polymer chain. So, that is the prediction of this reptation theory or reptation model. Experimentally, it has been observed that this kind of relaxation time to which reptation time corresponds to, that scales as m to the power 3.4. So, if we go back to the previous lecture, last lecture, there we discussed that for the Rouse kind of motion, the characteristic time actually scales as just n. So, here in the case of reptation, the reptation model predicts the time to scale as m cube, whereas the experimental prediction is m to the power 3.4. So, we see that the exponents are not that different, one is 3, one is 3.4. But quantitatively, of course, if we try to obtain quantitative data, that will be different because of the almost 10% or 15% different in exponents. So, reptation model captures the behavior to some extent, but we will discuss later there are some deficiencies in the simple reptation model, because of which this exponent is not accurately captured. Okay. Now, we can, if we consider the entanglement strand, so we can define characteristic relaxation time for the entanglement strands of the polymer chain as well, and that we can define as represented as tau e, which will be given by this expression, and we can use this expression here because an entanglement strand is the region of polymer chains between two entanglement points. So, the characteristic relaxation time of this entanglement strand can be described using the Rouse model, because the entanglement strand itself is a portion of the chain that has a size smaller than the length scale of our the presence of entanglements. So, this Rouse time of our entanglement strand with which contains any monomers from the Rouse model, that we can write simply like this, and this tau e this time can be thought of as representing a time characteristic time beyond which a polymer actually becomes aware of the presence of other constraining polymer chains in its neighborhood. So, if we are observing the polymer chain motion at a time scale below this tau e, which is the Rouse time for the entanglement strand, then the polymer chain actually will not at this time scale be aware of the presence of constraints around it, but above this time tau e, if we are making observation at a time scale larger than tau e, then of course the effect of entanglements will be present. Now, if we consider, so this tau e again from previous lecture we can simply write as tau naught times Ne square, where tau naught is a Kuhn monomer relaxation time. Now, we can consider the ratio of the reptation time and this Rouse time for an entanglement strand, and if we take the ratio of this and this, and if we simplify, we will see that it is of the order of n over Ne cube. Now, this n over Ne, this just represents the number of entanglements present along a given chain, right. The chain contains n number of Kuhn monomers, a given entanglement strand contains any number of Kuhn monomers. So, n over Ne will be the overall number of entanglements present along a given chain. So, we see that the reptation time over this tau e, that scales as cube of this number of entanglements present along the polymer chain. So, now let us consider the motion of the polymer chain again. So, the time scale that is defined by the reptation time, we discussed that this time scale corresponds to the time over which the polymer chain moves a distance equivalent to its own size. Okay. So, it is the characteristic relaxation time for the entire polymer chain in this reptation model, because this is a time scale over which the polymer chain is moving by a distance that is equivalent to its size. For the entire polymer chain, the diffusion coefficient we can simply write as some square of some length scale divided by this reptation time, and that square of the length scale is basically the length scale that is traversed by the polymer in this reptation time, and that, as we discussed, is the size of the polymer chain. So, we can the diffusion coefficient for reptation we can get as just r square over tau reptation, that is what we have written here. So, the diffusion coefficient of the chain in this reptation model is just the square of the some characteristic polymer size, which can be the end to end distance, divided by the reptation time. So, this is the order of the diffusion coefficient of the chain, and this diffusion coefficient corresponds to the diffusion in the entire entangled polymer melt and not inside just the confining tube. So, previously we had also used that curvilinear diffusion coefficient that corresponded to the diffusion of the chain just within the confining tube. But if we are looking at the overall picture, then the polymer chain as it diffuses through the entangled melt, that diffusion coefficient of the polymer chains in that system, that will be given by this expression. This polymer, if we consider the size of our polymer chains, we can say that it is A square times n over Ne, and this is again something that we have already discussed in a slightly different form previously in this lecture. So, and this tau reptation, the expression tau reptation also we have discussed a couple of slides back. So, if we take these two expressions, one for r square and one for the reptation time, and we substitute both of those expressions here, then the expression for the diffusion coefficient in this reptation model reduces to just this, where apart from taking the ratio, we have also made use of the fact that A square by B square is equal to simply Ne. So, the diffusion coefficient for reptation, we see it scales as reciprocal of n square, or equivalently it will scale as reciprocal of m square, where m is the molar mass of the polymer, because the n, which is number of Kuhn monomers, and m, which is the molar mass, they are directly related. So, what we can say is that in this reptation model, the diffusion coefficient scales as reciprocal of m square, or m to the power minus 2. So, that is the prediction of this model. Experimentally, it has been observed that the scaling is again a bit stronger. So, the exponent is minus 2.3 experimentally observed one, whereas the predicted one is minus 2. So, we still again see some discrepancy, although it is able to capture the dependence to some extent, but there is some discrepancy in the value of the exponents between prediction of reptation model and experimental findings. So, now if we look at the different time scales that are involved in this reptation model, this tau reptation, and if we try to compare them, then this reptation time tau rep, that corresponds to the relaxation time of the entire polymer chain in the reptation model, and it is related to tau naught, which is the smallest relaxation time that we have, that is the relaxation time of a single Kuhn monomer. So, the relationship is something like this. These things of course can be obtained using the different expressions that we had written for the reptation time and tau e and others. The reptation time is related to the Rouse time for an entanglement strand tau e by this expression. So, earlier this factor 6 was not there, but we already have discussed that tau rep by tau e, that is of the order of this. So, this factor 6 is something that makes that is a constant prefactor, but the dependence is over n over n e to the power 3. And finally, if we consider just the Rouse time of the entire chain. So, this tau is the Rouse time of a single entanglement strand, which is a portion of the chain. Now, if the Rouse time of the entire chain tau r is considered, then that is related to the reptation time using this expression. So, again what we can say is that the reptation time by the Rouse time of the entire chain is just given by this ratio n over n e, and n over n e is again just the number of entanglements present along a given polymer chain. So, this Rouse time will correspond to a characteristic relaxation time of a polymer chain if no entanglements were present, okay. And reptation time is relaxation time of the entire polymer chain when entanglements are present. So, we see that due to the presence of entanglements, the reptation time actually increases, it is higher than the Rouse time, and the characteristic relaxation time of the polymer chain becomes longer than if entanglement effects were not present. Now, this reptation model was mathematically and rigorously solved by Dewey and Edwards in the 1970s, and will not go through any detailed mathematics of that, but we will just identify a couple of results that come out of the solution and discuss that, particularly from the point of view of viscosity. So, now from the solution of this reptation model of diffusion by Dewey Edwards, the expression of viscosity that is obtained is this, where G, as we discussed earlier, is the plateau modulus and tau rep is the reptation time. So, from here what we can say is that this viscosity is of the order of G times tau rep. This is just a constant prefactor. So, if we are considering just what is the order of this viscosity of our melt, then that will be the product of these two, and G, this we have already discussed earlier, is given by a certain expression, tau rep expression we have also discussed. So, if we combine both those expressions and simplify, then the expression for the viscosity obtained is this, and again we see that the dependence of viscosity on number of Kuhn monomers or equivalently on the polymer molar mass is of the power 3 type. So, if we again compare that with experiments, then the prediction of this model is that the viscosity scales as molar mass to the power 3, because again molar mass and the number of Kuhn monomers, they are directly related. So, we can write this, and experimentally viscosity is observed to scale as m to the power 3.4. So, again there is a small but non negligible discrepancy between the exponents. So, from these results what we see is that the reptation model is a good model for a good simple model for describing effects of entanglement in polymer melts, and it does predict some results which match reasonably with experimental findings, especially in terms of how, let us say, viscosity or diffusion coefficient scale with the molar mass. But the exact scaling is not captured by this model, and a couple of reasons why that happens is that one of the reasons is that in an actual case the confining tube length also can fluctuate. Okay. So, the contour length of the confining tube that can change, and that part is not captured in the simple reptation model of Dijon. So, that is one factor which leads to a discrepancy. And the other factor is that if we are talking about the given polymer chain constrained by many other polymer chains surrounding it, so the other polymer chains surrounding it are also mobile, they are also moving around. So, after some time, at a given time, if a polymer is surrounded by a certain number of chains, after some time some of those chains would have moved out of a region near it, and some new chain might have come in. So, this kind of phenomenon is referred to as constraint release, and this also is a factor which affects the polymer dynamics. So, these couple of things, one is the fluctuation in contour length and the other is constraint release. These are not captured in the simple reptation model of Dijon, and that is why the results that we obtain from this model are slightly off compared to experimental results. But still the reptation model is a very good description of entangled dynamics of long linear polymer chains in a melt, and it is a simple model and it reasonably well captures a lot of qualitative phenomena. So, it is a good model in that sense. So, here we will conclude our discussion of polymer dynamics, where in the previous lecture we talked about the dynamics of unentangled polymer chains, whether it is the short polymer chains in the melt state or polymer chains in dilute solution, and today we discussed the dynamics of entangled polymer chains. So, we discussed different models which are applicable to different cases. We discussed the Rouse model, Zim model as well as the reptation model today, and we also discussed the different kinds of characteristic times which are associated with the different relaxation of different parts of the polymer chain. So, the longest relaxation time will correspond to the relaxation of the entire polymer chain, but relaxation of small segments or different segments of different lengths of the polymer chain, they will also have their own characteristic relaxation times. So, with that let us conclude our discussion of polymer dynamics, and it must be mentioned that what we have discussed is very preliminary, and it is just the surface of this entire subject, and if someone is more interested, they are referred to a very excellent text, a book by Dewey and Edwards, which is named Theory of Polymer Dynamics. Thank you.